Thanks so much for coming back for the last talk of the day. We've got Tatsuki Yamaguchi, who's talking about pure singularities and equal characteristics zero. Thanks for the introduction. I'm glad to give a talk here. Thank you for the organizers. Karen's work inspired me a lot. Thank you for Karen. Thank you, Karen, and happy birthday. Let's start my talk. This talk, we discuss this problem. About singularities, descent, and Yamaguchi. There are some known results. The result is due to Buto. So singularity descent and Yamaguchi. Recently, Chang showed that activity type descend under pure morphisms. Q-Gorenstein case is due to scattering. Another result is due to about dual singularity. And this result is the generalization of Kovacs result. Kovacs shows the split case. But the Lockham case is open, and this is the main problem of this talk. In this talk, we show the following theorem. Let RS be a Q-Gorenstein normal rings essentially over finite type over C. And suppose that the morphism from R to S is pure, and also suppose that S is of the self-pure type. Then R is also of the self-pure type. So I explain the definition of self-pure type. For local ring essentially for finite type over C. That is of density type. If reduction model P is clear for infinitely many. So the defining equation is have integer. If the defining equations have integer coefficients, this is the definition. And if the defining equations have don't have integer coefficients, more complicated. Definition is more complicated. An important result is this. This is shown by this is shown by Watanabe. If a ring is Q-Gorenstein and Q type, then the ring is has mechanical singularities. Compass is also expected, but it's open problem. Okay. Next, I want to use ultra products, so I explain the definition of ultra products. So, let P be the set of all prime numbers the a subset of the power set of P is called a non-principal filter is there exists two values finitely additive measure. The force P has is a one and any finite set has is a zero. And F is subset of P such that A has is a one. This is not the usual definition, but equivalent to the usual definition. So for any infinite set, non-principal vector filter exists because of Thorne's lemma. let's find their property. And so we say phi p holds for almost one p. If so we fix non-principal computer and for property phi, phi p holds for almost one p if the set of p satisfies phi has measure 1. This is the precise definition.
Sorry, just one clarification. So, in your definition, there can be a countable set with measure 0, right? Countable infinite set with measure 0.
Yes.
Okay.
Sorry, this is relative to a fixed non-principal alternative.
Yes. It depends on if he is applying four rings. So here also we need to fix it. The product of AP is defined by this, and where I is the set of sequences which such that AP for 0 for most of B. An important proportion is the mutual product of algebraic closure of FP is isomorphic to C as fields. Not canonical. This is not canonical. Only let Rn be locally essentially confined type property. Then once we fix this F base parameter theta F and field isomorphism sigma, then we can construct, we can define approximations. Can we so we give a precise definition because of the time, but I give an example. If R is local is this local link is and as P is this local link, then a family of RP is approximation of R. Something like this. In this setting, we have natural homomorphism. So natural switch algebra homomorphism from R to R to 3. The ultra product of R P. Next. Here we can define ultra perfect closure. X F and sigma. Then ultra perfect closure is defined by defined as the ultra product of the perfect closure of RPs. And we say ultra is clear with respect to sigma if the morphism from R to the ultra perfect closure of R is pure. This is the definition. This definition depends on the choice of with the F and sigma. So the main theorem is the following. Suppose that is Q-Gorenstein normal local. Then R is of the extra type. If and only if there exists F and sigma such that R is required here with respect to this is the main theorem.
There be examples of ultrafilters and sigmas that where it's not? I mean, or is that the same as all as well? Or are there examples where it's not? Can you replace the exists with for all in the theorem?
If you take all but finitely many as set A, which is all but finitely, that should be.
All?
I'm just asking, do you have an example where it doesn't hold for some?
All is, I think all is correspond to
No, but there should be like ordinary and super singular in that way. Like you should have some F, which is like some co-finite set for which that should not be true, right? Right? Like also, yeah.
I believe the answer is no to the question I asked. So, that's okay. I'll move on. I think I could choose an ultrafilter where it wouldn't work, but it would still be infinite, or like,
yes.
yeah.
Okay, so we need to choose appropriate So such that RP is okay. So the query, the first term is the query of this. So, if we take appropriate f and s sigma, then we have a commutative diagram like this. If S is with FPR, then R is also with FPR and use the necessary. Okay. Next, sketch of proof of the necessary. Taking canonical covering. We may assume Q-Gorenstein. For to show this direction, we take one piece parameter theta that contains this set and so if the defining equations, if the defining equations don't have integer coefficients, we need to choose appropriate sigma. But if the defining equations have the integer coefficients, any sigma is okay. For each direction, we need to take of course we need to take x sigma such that R is equal to 4 with respect to x sigma. So in both cases, we have a commutative diagram. This. So it is enough to show inductivity of R bar is equivalent to the inductivity of delta. So if we take generator of the software, this is mapped to a generator of the software. We can solve this. So hence this enough to show is equivalent to the integrity of U by E. Explain this injectivity. When it's this is it. Take X, take a P standard SOP for this is defined by from that is X is a system of parameters and each xi satisfies x satisfies this condition. Here A is the M is a product of analogators of local cohort. Suppose that L of this module is mapped to 0. X here X is the product of X. This is so this function is equivalent to CYP is in here. Here we use PP standard. So the perfect closure is usually not big coin module. So SOP is not a regressive standard. This condition is a bit complicated, but if we use P standard SOP, we can easily calculate it and easily calculate and so this condition is can be easily translated to this and this condition is about finitely generated idea. This is we can show that this containment so this shows eta equals 0 and done. Okay. Okay. That's all. Thanks for listening.
Questions? Yeah.
That middle step there, like the equivalents on the top of the board there, that's only for almost all P, right? Or
Yes, because all notions is defined and modulo almost all, and because we take the quotient.
Many questions? So. Oh, yeah.
That means assuming the weak ordinary, if you believe the convex set, then you prove that for log canonical the direct sum and of
So,
yeah.
assuming the equal condition, you can direct sum of local singularities is also
Asking the Q-Gorenstein, please.
Yeah.
I didn't hear the question.
What was the question
So the
again?
question was, if you assume weak ordinary, then if you that direct sum and of log canonical is log canonical. Assuming Q-Gorenstein.
assuming Q-Gorenstein is.
You're saying if you assume that log canonical applies.
No, assuming weak ordinary.
Assuming weak ordinary.
Oh, right, yeah.
Yeah.
R is correct.
You have to assume that log canonical
Assuming.
they don't go in 48.
If you replace the 1 over p to the infinity with 1 over p, does that like weaken the condition for ultra F purity? Or
This question. But it's weak. It's a thing.
like in the definition of ultra F purity, you have to quote it's ultra perfect closure. Can you just replace, instead of going to the ultra limit of r 1 over p to the infinity, you just do r 1 over p? Is this
I think essentially the same. The proof is essentially the same.
oh, it's the same. It's an equivalent way.
And maybe what Olivia was asking at the time, for almost all P does not mean all but finite unity. It just means for finite unity. Almost all.
for a set of P that's in the ultimate.
Define.
Yeah, the set of P's where you have the middle
Full
one.
measure.
But that doesn't actually mean cofinite.
No.
Yeah.
It doesn't mean cofinite.
Finite is practice, but the converse
Converse is not true.
is not true.
Thank you.